Identify whether the following compound has E or Z configuration. So we're going to look into this double bond and find out the two different groups that is attached to each of these carbons and find the relative priorities for the two different groups. Okay. So the first atom that it is attached to has a carbon in both of these groups. So this is more of a type. Then we have to focus on the other atoms it's attached to. So this carbon is doubly bonded to oxygen, to one oxygen, and it's singly bonded to another oxygen. So we can imagine that each of these double bonds can be considered to be singly bonded to one oxygen. So therefore, here it's going to be oxygen, oxygen, oxygen. So we can imagine that this carbon is connected to 3 oxygen for finding the relative priorities. And let's go on to this carbon right here. This carbon is attached to 2 hydrogens and an oxygen. So these are the 3 bonds that it's connected to. So now between these two, which one has got higher priority? Obviously, it is going to be this group. Let's go on to the other carbon. So for this carbon right here, you can see that there is a CH2 group here and also a CH2 group here. Now this is more of a type, so which case you have to see the other atoms it's connected to. So let's focus on this atom, which is the adjacent atom that's connected to this carbon. So here it is connected to this carbon, has an hydrogen, and it is connected to a carbon on this side and also a carbon on this side. So it's going to be carbon, carbon, hydrogen. But for this carbon right here, the adjacent carbon is this one, but this is attached to 2 hydrogens and a carbon. So this is going to be hydrogen, hydrogen, carbon. So between these two, which one has got higher priority? It is this one. So because the two groups are on the two high priority groups are on the same side of the molecule, if you divide this molecule into half, both the groups are in the upper portion, and therefore this molecule is cis or Z. Let's go on to the next problem. Draw the structure for the molecule below. So here it says secondary butyl, tertiary butyl, acetylene. Let's draw the acetylene molecule. So this is the acetylene molecule. And we have to substitute each one of these hydrogens with these two groups that's given here. So we need a secondary butyl group and a tertiary butyl group. So let's replace this hydrogen with secondary butyl group. What is a secondary butyl group? So a secondary butyl group is something where you have this carbon to be attached to a secondary carbon. So which means it should have only one hydrogen, and you still need to have 4 carbons, right? So this is going to be a secondary butyl group. And on the other side, you need to have the tertiary butyl group. So replace this hydrogen with the tertiary butyl group. So this carbon right here is a tertiary carbon. And similarly, this carbon right here is a secondary carbon. And you can see that each of these groups has got a total of 4 carbons. So therefore, this is going to be secondary butyl, tertiary butyl, acetylene. Draw the curved arrows to show how this molecule will react with HBr to form a carbocation. So what are we going to do for this molecule is we are going to write the actual structure of this molecule. So this is going to be the actual structure of the molecule. The one that is being represented here is the condensed structure, but this one is the expanded version. And when this reacts with HBr, okay, we know that it's going to form the carbocation. So where we'll be applying Markovnikov's rule, because this is an unsymmetrical alkene. So the electrons from the double bond is going to go abstract this hydrogen, and the Br is going to leave. So make sure that you always start the arrows from the electrons and point it towards the atom. Okay, and in the next step, it's going to form the carbocation. Which of these carbons is going to have the positive charge? Remember, according to Markovnikov's rule, the hydrogen is going to go to this carbon. And if the hydrogen is going to go to this carbon, then this is the carbon which is going to lose the double bond, right? Lose the pi bond. So therefore, it will be having only 3 bonds, and therefore this is the carbon that will be having the positive charge. Okay, so this is the carbocation that will be formed. What is the major product that is obtained when the following compound is reacted with H2O in the presence of acid? Also draw the mechanism for the reaction. Okay, so here we are going to do pretty much the same thing, but we are going to see whether there is going to be carbocation rearrangements happening in the reaction. Okay, so here we are going to add water, but this is happening in the presence of acid. So this is basically acid-catalyzed addition of water to an alkene. So in the first step, remember, the double bond is going to make a nucleophilic attack on this hydrogen, and one of these carbons is going to get the hydrogen. Right? Since there is equal number of hydrogens on both of these carbons, there is no preference. So you have the ability to form both of these carbocations. So here are the 2 carbocations that are obtained, and both of them are secondary. Now, each one of these can be attacked by the nucleophile to give the different products, right? But this molecule wants to see whether it can be converted into a more stable carbocation. So for which we have to look into either 1 to hydride shift or 1 to methyl shift or both. Now, if you take a look into this, this is a cyclobutane molecule, which is a highly strained molecule. So it wants to see by doing a 1 to methyl shift, it can be converted into a more stable structure. So this group right here can shift to its neighboring position. Thereby, it can form the 5-member ring structure. So when it does so, this is the product this is the new carbocation that will be obtained. Okay, this is a new carbocation, which is definitely a 5-member ring structure, which is definitely more stable than the one that we got here, right? And now your H2O molecule will act as a nucleophile on this, first giving rise to our protonated alcohol. And then another molecule of water will go and abstract this hydrogen to neutralize that positive charge to get our final compound, which is an alcohol. So this would be the major product because it is the most stable structure, right? Like you have the 5-member rings to be the most stable structure. But there could also something else that could happen here. Remember, this is a secondary carbocation, and this is also a secondary carbocation, right? But it wants to see whether there can be 1 to hydride shift. There is a hydrogen that is in the adjacent position. So this hydride can shift to its neighboring position, and it can be converted into a tertiary carbocation. So this is a tertiary carbocation. Okay, where this hydrogen or this hydride ion is shifting to the nearest position. So once this tertiary carbocation has been obtained, it can further react with water molecule and do exactly the same thing to give our product, which is going to be another alcohol, which is exactly the constitution isomer of this. So we have this product and we also have this product. Okay, between these two, which one is going to be the most stable product? Obviously, it is going to be this one. Although we form a tertiary carbocation here, and leading to the final product. This is the one which is going to be more stable because it resulted in the formation of a more stable 5-member ring structure. Okay, and you can also have some of the other product where the water molecule can go and attack this, okay, and we'll have an OH group right there, but that would be a really minor product. So this is going to be our major product, and this one would be the minor product, and this one would be considered as a trace amount of. So if there is going to be a water molecule that comes and attacks this, then the product that will be obtained from that is going to be like really trace amount of the product. What are the products obtained for these reactions? Now here is an alkyne. What happens when an alkyne undergoes hydroboration reaction followed by oxidation? So we know that it's going to give us either a ketone or aldehyde depending upon the substitution across the triple bond, right? So this is an internal alkyne, in which case it's going to give us ketones, right? So to begin with, let's see what's going to happen in the first step. So we have this alkyne. When hydroboration happens, which is basically we are adding BH3 in the presence of THF. THF is acting as a solvent. BH3 is going to get separated as BH2 and H, right? So where our electrophile is going to be BH2 and the hydride ion is going to be our nucleophile. So this is going to follow the syn addition where the BH2 is going to get added to one of the carbons and the hydride ion is going to get added to the other carbon. So here there is no preference, right? There is no, because none of these carbons have got any hydrogen, so there is no preference. If the BH2 is going to get added to this carbon, this is the carbon which is going to have the hydride ion. And it can also do the other way where the BH2 is going to get added to this carbon and the hydride ion is going to get added to here. So let's write down both the products that we'll be getting here. This is the product that's obtained in the first step, which is hydroboration. Now this reaction needs to be followed by oxidation. So when they are followed by oxidation with hydrogen peroxide, each one of this BH2 is going to get converted into OH. These structures right here is called as enol. Enols are unstable, therefore it will get converted into the keto form. Right, so where you will be putting the new double bond between the carbon and oxygen, and this carbon, which is losing the pi bond, is going to have an extra hydrogen which is gathered from here, right? So it's going to result in the ketone, okay, which is going to look like this. So you have a CH3 here, right? So in all of this you have a CH3 here. So you can see that these two products are definitely different. This is 2-pentanone, whereas this one is 3-pentanone, right? So if you go from left to right, making sure that the carbonyl group gets the lowest possible number, because that's the functional group. This is 2-pentanone, whereas this one is 3-pentanone, right? And when it comes to acid-catalyzed hydration, it is also going to result in exactly the same product. Right? What happens in an acid-catalyzed hydration? Again, it can directly add the hydrogen and OH, right? So if the hydrogen is going to go onto this carbon, this is the carbon which is going to have the OH, and you will have a double bond right there, and that will be the enol form. And because there is no preference, each of these carbons can choose to have the OH group, and accordingly you can form the 2-pentanone and the 3-pentanone compounds, both of these compounds. So even for this reaction, you get exactly the same products. Show the retrosynthetic analysis and the synthesis for the compound below. You may choose any starting materials which has 2 carbons or less. Now, since they have already said that we can only start the reaction which has only 2 carbons, we can choose acetylene to be our molecule. So we have to convert this acetylene into this geminal dihalide. Right? When you say geminal dihalide, you have the halogens, the 2 halogens on the same carbon. Okay, so how are we going to do this? First, let's take a look into this this starting material. It has only got 2 carbons, but here we have 3 carbons. So at some point, we have to form the acetylide ion to add enough carbons, right? And the fact that it has this geminal dihalide tells us that we have to do the hydrohalogenation, 2 times of the hydrohalogenation. So let's do the retrosynthetic analysis for this compound. Let's say that we are going to break this target molecule into different synthetic precursors, so we can propose a synthetic route for this molecule. So if you consider that these are the 2 carbons that's originally in your acetylene molecule, then we can definitely perform the hydrohalogenation if we have a triple bond there, right? So in that case, we can imagine that this is the new carbon that's been added. So if you have a molecule that looks something like this, then we can easily perform the hydrohalogenation of this molecule to give this molecule. But can this molecule be prepared from acetylene? Yes, of course, it can be prepared from acetylene. So this would be the retrosynthetic analysis for this compound. Now let's draw the synthesis. So for the synthesis, we are going to start from acetylene. When acetylene is reacted with Na and H2 in the first step, it's going to give us this NaNH2 is going to act as a base, right, which goes and grabs this hydrogen, and the bond between carbon and hydrogen is going to break, and it's going to move on to the carbon. So that's going to give us the acetylide ion, and once the acetylide ion is obtained, we can then form the carbon-carbon single bond. Since we are missing 1 carbon here, we are going to add that carbon through the acetylide ion, being through the nucleophilic substitution of the acetylide ion on the alkyl halide. We are having 1 carbon less, so therefore we have to take methyl bromide. So this is going to make a nucleophilic attack on this electrophilic carbon, and the bond between carbon and Br is going to break, and this is going to result in the substituted methyl substituted acetylene, so which is exactly the same as this, right? And this is the new carbon that's been added, new methyl groups that's been added. So once you have the right number of carbons in your molecule, then all you're going to do is you're going to do the actual synthesis. When you do the hydrohalogenation, so you have to do excess of hydrohalogen, you have to take excess of HCl, right? So it can do the two subsequent electrophilic addition reaction. So here there is a preference where the hydrogen is going to get added, right? Because between these 2 carbons, this is the carbon which has at least 1 hydrogen, but here there is none. So the hydrogen here is going to get added to this carbon. So with the first electrophilic addition reaction, you will be forming the haloalkene. So and when you do this one more time, when you do the HCl reaction with HCl one more time, it is going to lead to the formation of the product, where the hydrogen is still going to get added to the carbon which has the most number of hydrogens. Since this is the carbon which has 2 hydrogens, the new hydrogen is going to go onto this carbon, and it's going to lead to the formation of the product. Let's go on to the next one. Show how trans 3-heptene could be synthesized starting with ethine molecule. Let's first draw the structure for trans 3-heptene. So we need to go draw an heptene molecule, which means like it needs to have 7 carbons. So 1, 2, 3, 4, 5, 6, 7. Okay, and the double bond should be between 3 and 4. So this is going to be trans 3-heptene. Now we have to start with ethine, right? So how are we going to synthesize this molecule from ethine, which is basically acetylene? Okay, now again, let's take a look into the starting material and the target molecule. Here you have only 2 carbons, but here you have a total of 7 carbons. Now, if you consider that these are the two carbons from your acetylene molecule, then we have to add the remaining portion, which is this one and this one. So you have to add a total of 2 carbons here and 3 carbons here, with a total of 5 carbons, right? And so to begin with, we can start with acetylene. And the first case, we are going to use NaNH2. And we have to add, you can choose to add 3 carbons or choose to add 2 carbons first, either way. Okay, so that's going to put the ethyl group on one side of the carbon-carbon triple bond. And you will perform this reaction one more time. But this time with propyl bromide. And that's going to put the new carbon-carbon single bond on this side. So once you have this molecule, then you have to reduce the triple bond, right? And since we need the trans alkene, we have to do this reaction with sodium or lithium and liquid ammonia. If we use Lindlar's catalyst, then it's going to result in the cis configuration. But since we need the trans, we have to use this reagent. And that's going to give us the trans alkene. Let us go on to question number 6. Draw the products for the following reactions. Here is an alkene which is being brominated in the presence of light. So this reaction is basically radical substitution reaction where one of the hydrogens has been will be replaced by a bromine radical. Radical substitution reaction. Alkenes do not normally undergo many reactions. The main reactions that they would undergo is radical substitution reaction and combustion reaction. Here you can see there are 2 different types of hydrogens. So this is one type of hydrogen, and these hydrogens, there are totally 9 hydrogens which can be replaced with bromine, and these are the second types of hydrogens. Now between these 2 different types of hydrogens, which hydrogen can be replaced by a bromine radical? For that, we have to look into the relative rates of the alkyl radical formation by bromine radical. So it's going to follow this order, where the tertiary can be formed 1600 times much faster than the primary radical. Okay, so you can definitely tell that the bromination is a selective reaction where only this hydrogen can be replaced by bromine. So therefore, the product is going to be this. Let's go on to the next reaction. We have a cycloalkene molecule reacting with NBS. What is NBS? NBS stands for N-bromosuccinimide. It's going to do the allylic bromination. Now let's find out the allylic positions. So you have this double bond here. So these are the vinyl carbons, and the allyl carbon is the sp3 carbon. So if you take a look into this, if this is position 1, this position 3 is an allylic position. And similarly, if you count in the other direction, this position 3 is also allylic carbon. So NBS is going to be famous for allylic bromination, where the hydrogen here is going to be replaced with a bromine here. So the product here would be this. Nothing is going to happen to the double bond. The NBS is not going to get added to the double bond. Instead, it's going to replace one of the hydrogens at the allylic position by a bromine. Remember, we also have an hydrogen here that can be replaced, but since this is going to lead to the formation of a tertiary radical, which is more stable, it's going to lead to this as the major product. whereas the other product is going to be the minor product. So this one would be the major, and the other product which is formed here would be the minor product. So this one would be minor. Let's go on to the next reaction. This is basically acid-catalyzed hydration of an alkene. Let's go on to the next reaction. The next reaction is simply an acid-catalyzed addition of alcohol to an alkene. So here we are going to follow the Markovnikov's rule. Between these two carbons, which one has got greater number of hydrogens? We can definitely see there is a hydrogen here, right? So the hydrogen, which is the electrophile here, is going to get added to this carbon, and the OCH3 is going to go to the other carbon. So the product here would be let us now look into the next problem. So this is our next problem. What is this reaction? This is basically radical addition reaction where the HBr needs to get added to a double bond in the presence of peroxide. Okay, in the presence of peroxide, a bromine radical is going to be generated, and that bromine radical is going to react with the double bond. Now, when you take a look into this reaction, look into the reactant, you can see there are two double bonds, one within the ring and the other one in the side chain. Between these two double bonds where the bromine radical is going to get added to lead to the product. Now, if the bromine radical is going to get added to the double bond, then it can only lead to the formation of, the secondary radical. So let's draw the product. So let's say your bromine radical has been generated and that has been added to the double bond. So it's going to lead to the formation of a secondary radical, which is going to look like this. But if the bromine radical is going to get added to this double bond, then it has a chance to produce the tertiary radical. Let's say here is your bromine radical, which is going to get added to this carbon. So if it gets added to this carbon, then you are going to form a tertiary radical, which is going to be this. So this is a tertiary radical that is created. So this one is a secondary radical. This is a tertiary radical. Since you form a more stable radical here, this can further react with HBr to abstract an hydrogen. To form the product, which is going to look like this. So this would be the final product. The next reaction is basically ozonolysis, where you will be cleaving this double bond and form two new carbonyl groups. Okay, so you can imagine there is a hydrogen here. So when this cleaves, part of it is going to form an aldehyde and part of it is going to form the ketone. Okay, so since this is a cyclic structure, you will only get one product. So at one side it's going to be an aldehyde and other side it's going to be a ketone. Okay, so let's write the molecule. So this part right here is going to be an aldehyde. Okay, and leaving that, you also have, let's say, 1, 2, 3, 4, 5 carbons, and the fifth carbon has a methyl group attached to it. So 1, 2, 3, 4, 5. The fifth carbon has a methyl group, and it also should have a carbonyl group because you are opening this ring. So this one should be your ketone. So here you should have a ketone, which is this. Okay, let's do the next reaction. The next reaction is the halogenation reaction. And it is also asking us to provide the stereoisomers. What happens when you do the halogenation of an alkene? Obviously, it's going to form the cyclic bromonium ion, right? Once the cyclic bromonium ion is formed, the other bromide ion is going to come in a direction that's opposite to that of the leaving group, right? Or opposite to that of this cyclic structure. And it's going to break open this ring. But it's going to result in the formation of the two enantiomers because this is an unsymmetrical alkene. So here anti-addition happens and the products are going to look like this. So if one bromine is towards you, the other bromine will be away from you. And you still have the remaining groups. So this would be one enantiomer, and you will also be able to form the other enantiomer. Question number 7. What is the major monochlorination product of the following reaction? Disregard stereoisomers. What would be the anticipated % yield of the major product? Now, if you take a look into this reaction, this is basically radical substitution reaction. Radical substitution reaction where one of the hydrogens in the alkane molecule is replaced with a halogen. Now, this is chlorination. So, for which we have to look into the relative rates of the alkyl radical formation from the chlorine radical. Okay, which is going to follow this order. You can see it is much easier to form the tertiary radical, okay, where the tertiary radical is formed 5 times much faster than the primary radical, whereas the secondary radical is formed 3.8 times faster than the primary radical. Okay, now if you take a look into this molecule again, there are 4 different types of hydrogens. So this is one type of hydrogen. You have 6 of those hydrogens, and you have this hydrogen that is definitely different, and these 2 hydrogens are different, and finally this methyl hydrogens are different. Okay, so you have 4 different hydrogens, which means when you replace each one of these different types of hydrogens with chlorine, you will get different products. Let's first draw the radicals that will be obtained, and from there we'll draw the 4 different products that we'll be getting. So to begin with, let's say that this is going to be a half A hydrogens. These 6 hydrogens are one and the same. I'm going to call this as A, and this is B, C, and D. If I'm going to replace the A hydrogen with the chlorine, then this is the radical that I'll be getting. And similarly, I'm going to remove each one of these hydrogens and convert that into radicals. So these are the different radicals that has been obtained by abstracting each one of these different types of hydrogens. So this one is a primary radical. This one is a tertiary radical. This one is a secondary radical. This one is again another type of primary radical. And we can also write down the 4 different products that you'll be getting. And here are the 4 different products, and you can see that all of these compounds are different. Okay. Now, what would be the major product for this reaction, and what would be the percentages of these products that will be obtained? Okay, for that we have to do a little calculation here. We are going to multiply the probability and reactivity together and come at the percentages of these different products. Okay, so let's take a look into this. So this one is a primary, this is creating a primary radical. And how many, what's the probability for it to create that primary radical? So there are 6 hydrogens that can be abstracted, right? So the probability is going to be 6, and we are going to multiply it with the reactivity of the primary radical. The primary radical has a reactivity of 1, so we are going to multiply it by 1. So that's going to be equivalent to 6. Here, this has resulted in a tertiary radical. How many hydrogens can be abstracted here? There is only 1 hydrogen. So here the probability is 1, and the reactivity is 5. Remember, for a tertiary radical, it's equivalent to 5. So times 5. Let's go on to the next one. So this is a secondary radical, and how many hydrogens do we have here? We have 2 hydrogens here. So the probability is 2 multiplied by reactivity. What is the reactivity of the secondary radical? It's 3.8. So it's going to be 3.8. And for the next one, for creating this primary radical, you can have 3 hydrogens. The probability is 3. And then what is the reactivity of the primary radical? It's just 1, right? So 1. So this is going to be 6, and this is 5. This is going to be equivalent to 7.6, and this one is equivalent to 3. And we are going to add all of these numbers together, 6, 5, 7.6, and 3 together, and that has given us 21.6, from which we are going to calculate the total percentages for each one of these compounds. So this one is going to be produced in this percentage, where 6 should be divided by 21.6 times 100. So that's going to give us, when we do the math here, it's going to give us 27.7%. And for us, this one, it's going to be 5 divided by 21.6, which is going to be equivalent to 23.1%. And for the next one, it's going to be 7.6 divided by 21.6, which is going to be equivalent to 35.1%. And the next one is 3 divided by 21.6. It's going to be equivalent to 13.8%. So from here it is very clear that this is the one that has led to the highest amount of the highest percentage of the product, and therefore this is going to be our major product. So this is our major product. What is the major product of the reaction? Also draw the mechanism for the chain initiation and propagation steps of the reaction. So here is a radical addition reaction where the HBr will get added to the double bond, right? So in the presence of peroxide. So peroxide is going to initiate the reaction where it's going to form the bromine radical. So in the first step, which is the initiation, so let's have it here. The peroxide, let's draw the structure for peroxide. The peroxide is going to create as an alkoxide ion, where the weak oxygen-oxygen bond is going to break, and it's going to lead to the formation of an alkoxide ion. So once the alkoxide ion has been created, it's going to react with HBr to produce the bromine radical. So this is what is happening in the initiation step. In the next step, the propagation, the bromine radical is going to react with a double bond to form an alkyl radical. The bromine radical will react with this double bond to create as an alkyl radical. Now you need to find out like whether the bromine is going to get added to this carbon or this carbon. So if the bromine is going to get added to this carbon, then a tertiary radical will be formed. So you wanted to go for that, because if the bromine radical is going to get added to this carbon, then it will only lead to the formation of a secondary radical, which is relatively unstable. So we want to add the bromine to this carbon so we can form the tertiary radical. Okay, so this is one of the propagation steps. In the next step, what's going to happen is this alkyl radical is going to react with, is going to abstract an hydrogen from HBr molecule to give us the product. This is the second propagation step where you can see that the bromine radical has been generated, which will further go and react with another alkene to produce the alkyl radical and so on, and the reaction keeps going. Draw the products for the following reactions and also include stereochemistry. Now for this particular problem, what we are going to do is we are going to sort out the different reactions, like put all the like things together. So let's find out what are the reactions that's going to lead to the formation of carbocation. This is going to lead to the formation of carbocation, which is hydrohalogation, and this one is also going to lead to the formation of carbocation, right? So this is carbocation, and this is also carbocation. Are there any other reactions that's going to form the carbocation? No. And next, so whenever there is carbocation formation, it's always going to lead to the formation of racemic mixture. Next, we will go on to the reactions which is going to form the cyclic halonium-ion intermediate. So all of these reactions, this which is halogenation, this is halohydrin formation, and this is basically like you are having the alcohol as a nucleophile in the second step. All of this is going to form the cyclic halonium-ion, right? So cyclic intermediate, and this is also cyclic intermediate. Cyclic intermediate. And this is also going to lead to the anti-addition product, anti-addition, where the two groups that are getting added will be in the opposite direction. And then the next set of the reaction is the syn addition. So these two are going to be syn addition, right? Syn addition. Here it's going to be concerted reaction, whereas here the two hydrogens is going to get exactly added in the same direction on top of the metal catalyst. So now that we have sorted out the reactions, we are going to identify the products for this reaction. Let's go on to this first reaction with HBr. So we have a cis alkene. When it is reacted with HBr, we needed to apply Markovnikov's rule. This is an unsymmetrical alkene. The hydrogen is going to get added to the carbon which has the most number of hydrogens. So this is the place, this is the carbon where the hydrogen is going to go, right? And the Br is going to go here. When it does so, it's going to create as a chiral center. So this is a new chiral center that is obtained. And now because there is one chiral center that's being created, and the product is going to be a racemic mixture, right? Since it's a planar carbocation, you will get a pair of enantiomers for this compound, for this reaction. Okay, so let's write down the products. So with HBr, so this is one of the product that is obtained, and the other product is simply going to be the mirror image of this. Now let's go on to the next reaction. The next reaction is basically acid-catalyzed hydration. So what's the basic thing that we'll do here? We'll switch the bromine with a hydroxy group. That's it. The hydrogen and the OH are the two groups that are getting added. So this is what is going to happen with H2O, the presence of acid. Okay. So these are the only two reactions in this list where it's going to form the carbocation and lead to the product. Let's go on to the next reaction, next set of reactions. For the next set of reactions, we are going to draw the cyclic bromonium ion. The cyclic bromonium ion is going to be like this, right? And the Br minus, whichever is the nucleophile. So here in this case, the Br minus is going to be the nucleophile, but here it's going to be the water, which is going to act as the nucleophile. And here it would be the CH3OH, which is going to act as a nucleophile. So just the nucleophile alone is different in the second step, but it's going to lead to pretty much the same stereochemistry. Okay. So let's write down the products for these. So with Br2, CH2, Cl2, here is one of the enantiomer, and you can draw the mirror image of this, and that's going to lead to the other product. And you can see from here that the two bromines that are getting added are in opposite direction, right? And also this is with normal halogenation, but when you change this to a nucleophilic solvent such as water or CO or an alcohol, the only change that you will be making here is you will switch one of the bromines with the OH or OCH3. So that would be the change that you will be making. So that would be the only change that you will be making. So for all of these reactions, bromine with CH2Cl2, bromine with water, and bromine with CH3OH, exactly going to give you the same products, same like products with the same stereochemistry, but it's going to lead to like the second nucleophile, the nucleophile that's coming in the second step, it's going to be different. Let's go on to this hydroboration first. For the hydroboration, it's going to create two chiral centers. Now, why two chiral centers? We have to add an hydrogen, and also an OH. Which of these carbons is going to take the hydrogen? This is the carbon which is going to take the hydrogen, and this is the one which is going to take the hydroxy group. And you can see that there are two chiral centers, right? Because of this, it can produce a set of enantiomers. So let's write down the products here. So this would be one of the product, and when you take the mirror image of this, that's going to be the other product. And here are the two products, which is a pair of enantiomers for the hydroboration followed by oxidation. Let's go on to the last reaction, which is hydrogenation, catalytic hydrogenation. What happens in catalytic hydrogenation? In catalytic hydrogenation, you're going to add the two hydrogens, right? So when you add the two hydrogens, how many chiral centers it's creating? So this carbon cannot be a chiral center because you have two hydrogens. It is only this carbon which can be a chiral center. So this is your chiral center. So when it forms one chiral center, it's obviously going to lead to the formation of a pair of enantiomers. Okay, so let's draw the product here. So here is one product. The other product is simply going to be the mirror image of this. So this is for hydrogenation.